Okay, so I'll introduce our speaker today. He's going to be talking about multi-component prediction methods. Jacob Reynolds, he works out at the Hanford nuclear reservation site, or working with the waste out there. The 56 million gallons of the high-level nuclear waste that's in either single shell or double shell tanks. But it has a very fascinating origin and composition. You know, there's a large number of waste types, and Jacob Reynolds is working on characterizing this waste and for mathematical models that they're using. You know, he's very well published. You know, published 32 papers in journals, reviewed conference proceedings, and very active in the academic community. And you know, with 13 years experience as a manager right now, Jacob's going places and is going to be doing some great things there. So I'll go ahead and turn it over now. Let me go ahead and shift the screen ownership over to Jake and let him go ahead and go with that. So all right. So Jake, go ahead and share my desktop, and then we'll be able to see your screen.
All right. Share my there we go. All right, are you viewing my presentation now?
Yeah, that looks great.
That looks great. Okay. So I am Jacob Reynolds. I'm going to talk to you about some of the complexity of nuclear waste that we have here at the Hanford site, and some of the ways that we describe it mathematically, help communicate it, and just kind of help understand that complexity for a lot of different types of problems. And this presentation is really designed to be kind of a high-level overview of a lot of techniques and a lot of issues that we face because of this complexity. And if there's anything that anyone's really particularly interested in, we could do another webinar on a more in-depth application of this or interest area. I just thought a real kind of high-level area overview would be the simplest thing to do for this presentation that might get the most interest out of people. So one of the complicating factors that we have discovered in Hanford waste is what the mathematics community calls the mixture constraint, and that is that you have a mixture of components. The fraction of those components have to sum to 1, and switching to percentages doesn't relieve that constraint because percentages have to sum up to 100%, and there are a lot of mathematical consequences that aren't necessarily intuitive that come out of that. One of those is that you can't change the concentration of one constituent without changing the concentration of other stuff. Just because if you add sum of 1, then you dilute out all of the other things. That means it's difficult to determine if a change in the property is due to the increase of one constituent or the decrease of another constituent. It just makes it difficult to work that out. This also invalidates a lot of statistical methods that are standard that you learn in statistics class for mixtures, because most of those methods assume that all of your factors are independent of each other, and if composition is one of your factors, that ends up invalidating that because the composition components aren't independent of each other. In thermodynamics, if you think back to PChem or chemical engineering thermodynamics, you may have had a half a page in your textbook distinguishing between extensive and intensive thermodynamic properties of mixtures. This mixture constraint is sort of inherent in that distinction. And that'll come into play a little bit later on in my talk here. So what does this mean to you? The question I have is, does this mixture constraint, is this in view how you interpret data? This slide here, these two figures have the exact same data on them. And this y-axis here is a measure of how much a solid called vermiculite likes either calcium or ammonium. And what that measure means isn't nearly as important as the fact that these two graphs can be manipulated by how you define the x-axis. Now imagine you have a system where this solid has either ammonium or calcium on it, has ammonium and calcium on it, and another system where it has ammonium, calcium, and potassium on it. And so your binary system would be having, oh boy, let me, so your binary system would be the system where you just have calcium and ammonium. Your ternary system is the one that has calcium and ammonium and potassium. This y-axis is just a measure of how much the system likes ammonium relative, how much the solid likes ammonium relative to potassium. On this left side, I have defined the calcium mole fraction on vermiculite as being calcium over the sum of all three ions. And you can see when you do that, there's a big distinction between the binary and the ternary system. If you are writing a publication, you could probably then go and say that there must be some important structural consideration that having potassium around influences the relative energy of ammonium versus calcium. This right side is the exact same data, except we define the calcium mole fraction as the ratio of calcium over just calcium to ammonium. So you've normalized it to the two ions that are involved in the system. In this case, there's absolutely no distinction between binary and ternary system. And if you were trying to publish the same data, you could say, wow, isn't that interesting? Having a third ion in the system has absolutely no impact on the affinity. There are two ways to present the data that give you the exact opposite conclusion. One says that potassium has a huge impact. The other says potassium has no impact at all. I know which one's right, but I'm not going to tell you what's right. I'm putting this up to tell you that people need to think hard about how they present data and what this mixture constraint means to people when they interpret data. So my overview, my thesis that I'm going to cover in this talk is that high-level nuclear waste, it's a many-component system, and but this mixture constraint has to be built into that. So the part one of the talk, I'm going to have an overview of Hanford waste compositions. Then I'm going to talk about how this compositional diversity, what sort of questions does that lead us to have to ask about the waste? And then part three, I'm going to talk about some of the approaches taken or under development at Hanford to sort of answer some of these questions. So Hanford waste, there's a lot of it, 56 million gallons. To put your head around that, if a football field, that would cover a football field 155 feet deep. If you are a mechanical engineer, you would divide our waste into three types of waste: liquid waste, salt cake waste, and sludge waste. I'm a chemical guy, and so I like to define it more finely than that, and I'll talk about that more. So what are we going to do with this waste? This waste will ultimately be split into a high activity fraction and a low activity fraction. A high activity fraction will have the overwhelming majority of the radioactivity. The low activity fraction will have the overwhelming majority of the mass. Both of those will be ultimately vitrified into glass in separate facilities. We have to run a number of separation facilities and waste handling facilities to do that, which are primarily under design and construct mode at some level of detail at the moment. Some of these processes would be that we'll have to leach aluminum and chromium and phosphate from the solid phase. We'll have to remove cesium and other radionuclides from the liquid phase. We'll have to wash out salts from the solid phase with water. And we'll have to do a lot of evaporation of liquid as a part of our water management. So this waste has a diverse origin. We ran a lot of different processes at Hanford. Hanford is a site that was developed to recover plutonium from spent fuel. And because they ran these processes for about almost 50 years, they ran a lot of different processes as the technology progressed. I've listed some here, a number of processes that reran, large-scale processes that contributed to a lot of different, that contributed a lot of mass to the waste. There's also a lot of tiny processes that contributed a much smaller mass to the waste. Each of these most of these processes had multiple flow sheets, and so there were a lot of different waste types that came out of each of these processes. I put this here so you can see that each of these processes has at least one waste type, most of them 6 or 7. So that means that there is a lot of different waste types that ended up in the Hanford tank farm. Fuel, they had to strip, nuclear fuel has cladding around it. They use two types of cladding on this fuel, aluminum metal and zirconium metal, basically. Actually, they're slight alloys, but we talk of them in terms of aluminum metal or zirconium metal. Those had to be stripped from the fuel, and those created an additional waste stream and additional complexity. Once this waste got to the tank farms, we did stuff to it, which added more complexity to the waste. One of which is we did what was called cascading, where you dump waste into one tank and let it overflow into another and then overflow into another. And that created some fractionation within the waste because the large dense stuff would settle out in the first tank and the light stuff would end up in the last tank. We ran evaporator campaigns to crystallize out salts. We added ferrocyanide to remove cesium from some liquid wastes. We added Portland cement and diatomaceous earth to some tanks that were leaking to try to soak up those liquids. We've retrieved waste out of a number of older tanks and put them in other waste tanks, which actually changes the composition. My staff wanted me to have a set of slides just on that to show the complexity of that. That's something they're all involved with right now. I decided not to do that because there wasn't a lot of time. But and salt well pumping is something we did. We have a lot of older single cell tanks that we wanted to get the liquid out of those because if the tank leaks, then it leaks straight into the environment. So we did what was called salt well pumping, where you put a pump basically in a well in the tank and try to pump out all of the interstitial liquid out of this kind of sludge salt cake type material. And all of those changed the waste composition fairly dramatically on top of the initial variability that we had from the waste processing, from the fuel processing facilities. So how many different waste types? If you go and look at the literature, you'll find a lot of people have divided Hanford waste types differently. The source that I got this one from divided up into 34 different sludge waste types and 9 salt cake waste types. That variability, that 9 salt cake waste types, in my opinion, doesn't reflect the true variability because they tend to be defined by when they were created rather than what they are created out of. So the true variability is much larger than that. The liquid waste types have generally been all commingled at some level now, which you would think would decrease variability. And it does a little bit, but it also means we have a wide spread of compositions and total concentrations throughout the tank farm in liquids. What elements do we have in the waste? This is the Hanford periodic table. Everything that's sort of pink there is a chemical used in one of the processing facilities, and we have more than 1 metric ton of it. Any of this, I want to call that kind of a light bluish something or other, pastel. Those are fission products that were created in the reactors. And we have over 100 curies. A curie is a measure of radioactivity, and a 100 curies is a lot. And if it has both colors on it, that means that that element fit into both of those categories. You can see we have a fairly high percentage of the periodic table in our waste in high concentrations. Even the things that are white, we have trace amounts of most of those as well. In fact, we have pretty much everything from curium on down, we pretty much have at least some of the entire periodic table in the waste. Just so people, I mean, I'm not sure that people know what nuclear waste looks like. This is an example of a sludge tank. It kind of looks a lot like soil. Of course, if you look at our 34 plus waste types, you would sludge waste types, they would each one look a little bit different, but this is an example of one just to get your idea of what nuclear waste looks like. It's basically a fine grained particulate that's wet. This is the salt cake. So our liquids are very, very highly concentrated. We did that deliberately in order to save tank space. Back in the day, they would crystallize out salts. A lot of the salts are very soluble, and they would evaporate, so you could crystallize out even very highly soluble salts. One thing, if you look at over here, you can see this is a wall coming down, and the depth of the salt cake is a lot deeper here right next to the wall than it is down here in the center. And this is the theory is that this wall is cooler than the center, and so the salts are slowly migrating to this wall and growing up the wall. So that is a phenomenon that's interesting to me that we see in all of our salt cake tanks. So the range of concentration. This is some examples of some major constituents. I've given these concentration in micrograms per gram. That means that a million is a 100%. The lowest concentration is over here of that element. This is across our 177 tanks. You can see most of these constituents have 5 or 6 decimal places between the highest concentration we see in the waste and the lowest concentration. Huge variability from, if you take a look at, this is calcium, and you figure calcium's a cation, there's got to be an anion. That probably means this tank is almost pure some calcium salts, whereas other tanks have essentially no calcium. So that gives you an idea of how wide the concentration range of some of these things are across the tank. This is just some more. I just wanted to show you there are lots of things that have this range. And the variability is not just in the concentrations, total concentrations, but even within an individual waste, there might be 4 or 5 components that individually have more than 10 weight% of the mass. So this variability can lead to fairly complex chemistry. This is an example. This is the solubility of aluminum as a function of sodium hydroxide. And when you increase sodium hydroxide concentration, you increase aluminum solubility. This dotted line would be a pure system where you just had water, sodium hydroxide, and aluminum. And aluminum hydroxide solubility would follow this line. And at some point, you would start to precipitate out this salt called sodium aluminate, and its solubility follows this line. And that's what you have in a very simple system. This solid line is from a simulant test that a guy named Scott Barney did in 1976 that showed that in a lot of our waste tend to follow this line. So there's a huge shift, and that shift is caused by some of the chemical behavior and complexity in our waste. And the true cause of this shift is really not completely known very well. The cause in this shift from here to here is simply the fact that if you have more sodium salts, then you favor formation of a sodium salt. But this hydroxide has a more complex component to it that we don't completely understand at this point. And this is an example of a phase. We have a lot of constituents that have a very complex behavior here that are difficult to model. So heterogeneity, this is from one single salt cake. These are pictures of 4 different salts that we've identified in one salt cake. Each of those are more than 5 weight% of the mass of the salt. And so you can see that we have even within one tank, we have a fair degree of diversity in the composition. And now if you think about a mixing system, you have this phase here we call nitrophosphate. It's sort of a hexagonal kind of phase versus this phase here, which is shaped more like a piece of paper. Those things, their mixing behavior is going to be different from each other. And then, of course, particle size. I found a small one. This one is only 100 microns. These crystals grow to be several inches in size. Versus some of these needles, which on one axis are not very big. So if you think about the mixing behavior of this complex mixture, it's going to be different than if you have a single phase of spheres. And that complicates our prediction of mixing performance. So if you have this kind of variability, and you know that you have that kind of variability, what sort of questions does that cause you to ask? This is just sitting down, me brainstorming some of the questions that I know that I've been forced to ask that come from our compositional variability. One of which is we sample these tanks by taking a core segment, similar to a rock sample. You push a pipe into the waste and pull it out, and so you have composition as a function of depth at a single location. So you look at a particular core segment, a particular part of that segment. Does that segment more look like waste type A or more like waste type B? And how different is that waste in that layer in that tank from a similar waste of the same waste type in another tank? How do the components partition between phases when you process? How does the change in composition in a liquid phase affect the removal target by ion exchange? When we vitrify this waste into glass, you'll have a target glass composition for each waste. How far can you deviate from that glass composition and still make acceptable glass? Because it's hard to manufacture glass to a perfect specification. And can we extrapolate the behavior of one waste composition to another? Some of the key approaches that we use is we use standard phase Equilibria solubility models for solubility calculation. We found that those can be very complicated and computationally intensive for many component systems. If you're just trying to model a single composition for an application, you can have someone sit down for an afternoon and they can do that. If you're trying to put that into a flow sheet to model the entire mission treating all 56 million gallons of waste through 400 plus vessels, that becomes computationally intensive. Then we use what are called mixture models, which are exemplified by a book by Cornell. If you go and read the statistics literature on mixture models, you'll find that a disproportionate of the development of that branch of mathematics was driven by questions at Hanford. And a lot of Hanford people over the years were involved in developing that theory. And then there are what are called composition models, exemplified by Aitchison's book. This is a relatively new approach at Hanford that we're really kind of recently adopting and finding use for. So what are some of the key questions? A mixture model, that's really defined broadly as something that asks a question, how does a property of a mixture change with the composition of that property? So think of any property you want, viscosity, heat capacity, anything like that. A composition model is sort of the opposite than that. How does some property or external condition affect the composition? So, and phase equilibria models sort of tie both of those together. They were developed by physical scientists rather than mathematicians, so we can usually define some sort of physical meaning to those, and that makes a lot of people feel better, I have found. So those are sort of the classes of models that we've sort of embraced here. The first I want to talk about is Scheffe's mixture model. So Scheffe was a statistician in the 1950s. This is a very simple model. You have some property Y. that is a function of the concentration of your component I, and there's a coefficient that defines it. This is a first-order version. Of course, you could add an infinite number of polynomial forms onto the end of this. I want to talk about this very simple form because it's mathematically identical to the equation for partial molar properties of a mechanical mixture. So if your system can be defined by this, it's very easy to sort of understand what these coefficients mean. The AI is the value of your property when x goes to 1. And there are fairly complicated versions of these models, now, when you only have a few components, this can look like a simple model, but imagine having 50 components. Even a first-order version of that can have a very complex behavior. All right, I'm not sure why this is, there we go. The Scheffe mixture model, this is an example of some of the complex behavior. A lot of people want to say if I have a coefficient that is 0, that means that component has no effect. That's not so. That component still does have an effect, and we actually find a 0 for a lot of properties. You can find things that have a 0 coefficient. I just made up some numbers. And if you have a 3-component system where one component has a 0, another has a coefficient of 1, and another has a coefficient of 3, you set x2 equals to x3 to generate this graph. And then you look at what happens to your y when you change x1, which has a 0 coefficient, and you see that y still changes. And this is back to this mixture effect because even though x1 has a 0 coefficient, its presence changes the concentration of these two. So even if it has a 0 coefficient, it still has an effect on the system. All right. So the Cox mixture model, this is a little bit more complicated model that helps us communicate things. This you have a property I changed from y to p here. A naught is a value of that property at a target mixture composition we call S. So S is the concentration of y of x at a target mixture composition. And in this model, there's a constraint where all of these coefficients have to equal 0 so that p equals this value at y. This concept of a standard mixture composition is it's analogous to the concept of standard state that you see in chemical thermodynamics. We sort of use that a lot, where we have some composition that is, say, the current state, and we're interested in, when we do something that perturbs that composition, how does that change? So if you look at these coefficients here, this A coefficient is now the total change in the property P between your target composition and the pure component X. And so that has a fairly easy interpretation. Again, though, this is a highly simplified version. You could add an infinite number of polynomial terms to that. This is an example of sort of plotting the concept of a Cox mixture model. And we use this Cox mixture model mostly from a communication standpoint. This is the example of a viscosity of a glass as a function of the change in the concentration of several glass component oxides. So when we turn it into a glass, most of the components get turned into oxides because mostly everything that isn't a metal tends to decompose in the glass. So you have 0 is your target composition, and when you say follow sodium, a 10% change in sodium changes your viscosity value this much, whereas a sodium is a good example because it can change over a wide range, whereas fluoride cannot change that wide. But if you look at silica, a 10% change in silica has a much smaller effect on the viscosity. This allows you to communicate to people how a component is affecting the composition. Now, inherent in these lines are you are changing one component while the ratio or the relative fraction of all other coefficients are all other components are staying constant. So in this case, when you're following the sodium line, the concentration of sodium would be going up, and the relative proportion of everything else would stay constant to each other, but the ratio of sodium to everything else would go up. And so this is a type of graph we find useful for communicating to people the effects of components on mixtures. All right, this is so this you can think of there being a slope between your standard component and your pure component. This is just a mathematical equation. Everything in the brackets is the slope between your standard component and the pure component. In thermodynamics, this property is called a partial molar property for an intensive component. So if you think of it that way, you can add a theoretical interpretation to these otherwise empirical model. All right, does anyone have any questions? I haven't heard anything from everybody. I'm a little concerned that no one's hearing me.
No, we can hear you, Jake. I just have everyone on mute just so we don't get audio feedback. But
sounds good.
I actually just had one question on this part. You know, you have all of these different mixing rules, you know, that kind of started in the 50s and kind of built up, you know, with more complexity. And you know, do you ever find that you get local solutions to your, you know, you get more complex on your mixing rules, that you get mathematical solutions that you may have multiple mathematical solutions as you go to some of these higher order or more complex mixing rules?
We have not encountered many situations where you get a multiple solution for the same situation when you're solving the model, but sometimes you're using the model to optimize something, and there are multiple solutions to the model that give you an optimum composition. Like if you are trying to formulate a glass for a waste, and you would like to maximize the amount of waste loading, amount of waste you can put in the glass and still meet all of your requirements. And so I put up a model for viscosity up there. For that glass, we might have a lot of other properties we're interested in, like durability, melt rate, and things like that. And we have found lots of situations where there are multiple optimum solutions in a local area. And there might even be multiple composition, multiple glass former additions that give you the same optimal waste loading. And we see that all the time. For thermodynamic models, which use more complex functional forms than sort of the typical polynomial models we use in mixtures, for mixture models, we find local results all the time for those, and that's a major problem with a lot of the common functional forms that are being employed in electrolyte thermodynamics, is that they are subject to local solutions. And that there is some documentation of that in the literature, but most people in the literature are not solving as complicated a system as we are. A lot of people, you go look in a standard industrial process where they're modeling electrolytes, they may have 20 components, and a giant model to them might have 200 components. You know, we have lots that have 2,000 components, and so we are much more subject to those risks in our system than a lot of other people are.
Oh, interesting.
So, yeah.
Okay.
So, yeah. All right. So this slope, I talked about a slope between a target composition and a pure component. That has meaning. That's a partial molar property. And there's a lot of understanding of the underlying physics that you can gain from those coefficients. We have actually started putting that slope into models, and this is an example one. It's called the component slope linear model. This is a very simple first order model. This coefficient here is, again, the value of your property at your target composition. You have a much more complicated constraint. And this gamma I now becomes your partial molar property for component I. So if this were heat capacity, and this would be your partial molar heat capacity for X sub I. We have found a lot of times we get criticized for using empirical models, and they say there's no meaning to that. And there's a moral philosophy that empirical models are bad, and we use these to defend ourselves and say, look, there is actually some theoretical meaning embedded in these otherwise empirical models. So composition models, those are where the composition is sort of what you're modeling. You're trying to model a change in composition. So composition becomes your dependent variable. One of the things that Aitchison is sort of the father of composition models, and one of the things that he has pushed is because mixture components are not independent of each other, you can't really say anything about the definitive about the individual component concentrations. You can really only say anything definitive about ratios. And the early pioneers in chemical thermodynamics recognized that to some extent. You'll see that in most electrolyte thermodynamics, at least, they use molality, which is moles per kilogram of solvent. It's sort of the composition variable that they model. And they recognized that long before the statistics community came along. So, you know, we here in the chemical sciences are ahead of the mathematics communities in some cases. However, if you go and look at the modern statistical literature, they tend to use log ratios, and I will send you to that book by Aitchison to explain why. There are some good reasons for it if you're doing some types of statistical inference. One thing that I have found is when you use these log ratios that statisticians use, a lot of problems that we run into is you have a solid that is a solution. It's got multiple metals in the same mineral phase, and then the liquid is a solution. You have a lot of metals in the liquid phase that is in equilibrium with those solids. For some reason that I don't understand, that I suspect is mathematical rather than physical, there tends to be a strong correlation between the log ratio in the liquid phase and the log ratio in the solid phase. And this is the same solid that has 4 cations in it: sodium, calcium, potassium, and magnesium. This happens to be a phase called illite. And you can see that all 4 of these ratios, all of this solid is in equilibrium at each of these data points with all 4 of those. And you can see the ratio. There's a linear ratio between all 4 of them. And I've found this ratio to hold almost everywhere I look. Now, if you look closely, you could find some deviations right there, and these are actually the same data points right there for the different metals in the solution. But this just seems to be a very common situation that nature has presented us, and that makes it convenient to use these log ratios that the statisticians sort of want to push on us. So when you talk about a composition, one of the complaints of using log ratios or other ratios is you get from the physical scientists like me and a lot of you is, so what is a log ratio? What does the difference between a log ratio mean to me, especially when you have a difference between, if you have a 30 component system, what does the log ratio between 2 of those mean to me? How do I understand that physically? So one of the things that Aitchison came up with is a measure of distance between 2 compositions. And this here is the equation for that distance that he derived. This article, by the way, is a letter to the editor commenting on someone else's paper, and I know of no other paper, letter to the editor I've ever seen that has more than 100 citations. This is just a measure that they came up with to help you understand what a distance means in a composition. So how do you use this distance? So one of the things that we've made use of it for is it's a great measure between the difference of compositions. We found you have to screen that because just like a meter may be very important when you're on a football field, but it is not a very useful measure of distance when you are measuring the distance between atoms in a crystal structure. So you've got to have some way to calibrate that distance, and that's one of the things we found is we have to think hard. What does this distance mean to us? It's also a great measure of the accuracy of a model. If you're going to have a model that predicts a composition of as a function of anything, we use this Aitchison distance to sort of judge how accurate is that model predicting that composition. If you have a two-component mixture, it's easy to use standard Euclidean geometry to sort of understand how well am I predicting that. When you have a 30-component mixture, and you're predicting the concentration of all 30 of those components, you know, it's harder to judge what is the accuracy of that model. One of the things we've decided, if you are parametrizing a model that is predicting that composition, we think the sums of Aitchison's distance between the measured and predicted composition matrix is the best objective function to minimize, because Aitchison's distance is the best measure of distance between compositions. So, solid-liquid solubility thermodynamics. This is typical. There are a lot of sources you could go to look at to learn about this. Our big complexity is just the sheer size. One of the things that I own is the model in what we call the life cycle model, where we are trying to predict how we are going to treat all of the waste and the waste behavior throughout the entire mission of treating all of the waste. And we have thermodynamic models embedded in this life cycle model. The sheer size of our models, because of the large number of components and the large number of vessels, requires really efficient models. And that's something that we have not been really good at in the past, and we're really just starting to try to make more efficient models so that we can actually solve different potential mission scenarios in less than a week. So one of the things we're looking at is simple algorithms that you can use to sort of rapidly exclude some components from a flash calculation. And that's some of the approaches that we're looking at right now. An example that we are looking at, I know there's some people interested in sodium sulfate. This is the solubility of sodium sulfate in water. You can see as the temperature goes up, the solubility goes up, it gets an inflection point, and it actually goes down. The solubility starts to go down with temperature, and that inflection point is actually the temperature where you transition from different stable phases, the anhydrous sodium sulfate and sodium sulfate with 10 waters. So this is the sodium sulfate with 10 waters, and this is the anhydrous sodium sulfate right here. So in pure water, you have a well-defined transition temperature, and if you knew that you were below the transition temperature, then you would not have to include the anhydrous sodium sulfate in your model. If you knew you were above the transition temperature, you knew you would not have to include this component in your model, and that would make your model simpler and much easier to solve. One of the complexity, though, is when you have electrolytes in the system, that transition temperature changes. So here we have the transition temperature between those phases, and on the x-axis, weight percent of these example electrolytes. And you can see there's a pretty big impact from near freezing, you know, up to the transition temperature for pure water somewhere out here. So when you have a multiple component electrolyte system, this becomes a much more complicated situation to evaluate. But one of the things we're looking at is evaluating that. We found that the water activity is a really good predictor of that transition temperature. So in conclusion, Hanford waste has many components and a highly variable composition. The mixture constraint complicates a lot of mathematical modeling of this waste because the components are not interested in each other, and we're developing sort of a lot of different approaches, and these are some of the approaches that we're looking at in order to model the chemistry of this system. You know, I know we also have a lot of complexity with the physical properties, transport properties, I would say, that I didn't discuss here, but that is also a very fascinating complexity that we have to deal with here. And I say that because I know there's some people listening who are involved in that area. So, all right, I will take any questions. I went through that about 5 times faster than I did in any of the times I practice it. So we have lots of time here for questions.
Great. Well, thank you, Jacob. I thought that was a very informative discussion. I'm going to go ahead and open it up to questions. Feel free to unmute your microphone and go ahead and ask.
I have a question.
Sure, go ahead, Frank.
Because you're working with solutions of ionic solids and ionic solids themselves, I'm wondering if changes in the dielectric properties with composition are an important factor in some of these effects that you see.
Yes, they are some of the most important effects. Well, we have found that trying to understand what's going on with the dielectric properties are more difficult to understand than just trying to model the properties as a function of composition. So we sort of understand that changes in dielectric properties are part of the reason that we see what we see. But we tend to go straight to predicting the property of interest because we find that's a lot more economical on these, you know, highly complex systems.
Gotcha.
So that's sort of where we're at.
Okay, thank you.
Okay, great. We have time for maybe 1 or 2 more questions if anybody else has a question for Jacob. Okay, I have actually one question for you. You mentioned something at the beginning that was kind of interesting. The difference in temperature, the temperature gradient within the waste tank was maybe causing some separation to occur, or building up certain salt compounds. Is that going to be exploited when the waste is extracted and vitrified? That you already know that certain salt cake layers are going to be lower level in radioactivity, and so those can be separated out as low level, or what can you use about the heterogeneity of the tanks to have some sort of that pre-screening?
Yeah, so in your question is embedded actually a lot of questions. So the temperature effect, we are exploiting that to target specific components, like say aluminum. Its solubility is very temperature dependent, and so we're exploiting that temperature dependence to target aluminum, where you might have one phase you aren't interested in dissolving, is insoluble at that temperature, but aluminum is, and so we use that temperature dependence as a sort of separation tool. In terms of the complexity, and how does that play into optimizing the mission? One of the things we do is look at what waste types do we not want to blend together? What waste types would we rather treat by itself? And then there are other waste types that if we could blend them with off as much as possible, that would be great, because they by themselves are highly problematic, and if you can sort of dilute them out with other wastes, then you can solve a lot of the issues with an individual waste type. Mm. So I don't know if that gets at your question.
Okay. Yeah, it just depends on whether you want to blend or keep them separate for the different ways.
Yeah.
Okay, great. Let's see, any other questions from the audience here?
Yeah, I had one question. I joined a little bit late. I wanted to understand the distinction between the type A and type B waste.
Well, so type A and type B were two I use those as letters to designate potential waste types of the 40-some waste types that I mentioned earlier. We also have, I unfortunately used some letters that happen to also designate how likely a waste is to generate flammable gases, which is one of our largest safety, or I don't want to say safety concerns, but it's a lot of our safety controls are around controlling flammable gas buildup in our tanks. And type A tanks would be tanks that generate a lot of flammable gas, and type B tanks would be tanks that generate much less.
Okay, thank you.
So that would be an example.
Okay, great. Any last questions? Okay.
Just a question out of curiosity, Peter Small here. Can you comment on content uniformity in your tanks? Because I can imagine that if you would take samples from different parts of the tank, you may find very different conditions.
Yeah, that is absolutely right. And we have lots of variability within an individual tank, both vertical and lateral. So we have more vertical. A lot of the waste tended to be put in the tanks in layers. So you might have ran a process for a while and put one waste type in a tank, and you maybe only filled up that tank 15% of the way. And so a new waste processing came on, and you put in another 100,000 gallons with something else on top of that. And you may have done that 3 or 4 times. We have one tank I was working on yesterday that had 14 waste types laterally within the tank, or vertically within the tank. Laterally, a lot of the tanks were filled by on the side, and so the waste would be slurried into the tank coming in the side of the tank, and so the heavy stuff would tend to end up on the side near the intake, and the lighter stuff would tend to settle out on the other side of the tank. And so components that tend to be heavy may be on one side and light might be on the other, and that's something that makes determining the inventory challenging. Exactly. So, yeah.
Okay, great. And let me just go ahead and share our next webinars that are coming up. We have December 3rd, then on through in January, about one every week, starting in January. Thank you guys for joining. Thank you, Jacob, for presenting. I thought that was a very interesting, informative discussion about some of the challenges you face with these very complex wastes. So thank you again, and thanks everybody for joining, and we'll catch you guys for the next webinar.